Let's wrap up this section with one more example. Imagine we have a square-based rectangular box that has an open top and a volume of 32 inches cubed. Find the dimensions that minimize the surface area. So this is really interesting. Let's take a look at what we're looking at. We've got a box that's open on the top. The base is square, so that's really important because that simplifies this problem greatly. So I'm just going to call this value B for base. Square base means that it's base, 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 base all the way around. Same sides every time, so that's really good. And so let's think about what we know. We know the volume is 32 inches cubed. That's actually our constraint. The volume is equal to 32 cubic inches. And so that's our constraint. And so we know that the volume is the area of the base times the height. So what that means is 32 is equal to b squared h. Because it's base times height, but our two bases are the same, so we have base squared. We want to now minimize the surface area. So that is our objective function. The surface area, again, is an open top, so make sure you do not include that in your surface area. This is going to be base times height for that square, and we're going to have 4 of those. So 4 base height rectangles going around the edge, and then the base is going to be b squared, because the base is just base times base. So we have 4 of these BHs, and then 1 base squared down below. So there you go. There's our objective function right here. Here's our constraint. I did that pretty quickly, but hopefully it makes sense. This problem is a little bit trickier than the one we did before it. Now let's go ahead and solve for our constraint. So if I solve that problem for h, this equation, I get h is equal to 32 over b squared. And so that's good because that means that we will be able to plug that into our optimization. Here we go. SA equals 4 times b times, replace h with 32 over b squared plus b squared. So there you go. It's 4 times b times 32 over b squared plus b squared. If we clean that up a little bit, it'll be SA equals, this b cancels with that one. So 4 times 32 is going to be 128. So we got 128 over b plus b squared. There's our new optimization function in only one variable, so we can take a derivative and figure out the maximum and the minimum. Let's do that. The surface area derivative will be negative 128 over b squared plus 2b. Take a look at that. Make sure you agree with me on that. Set it equal to 0. Like so. Then we can multiply everything by b squared, which will leave us with 0 equals negative 128 plus 2b cubed. All right. Add the 128 over. We get 128 equals 2b cubed. Divide by 2, divide by 2. 64 equals b cubed. And happily, when we take the cube root, we get b equals 4. So if the base has a length of 4, then that means that we're going to minimize the surface area, which is really cool. And now we can figure out what our height is by plugging that into this constraint. So if I take my 4 and plug it in right there, I get 4 times 4 is 16. 16 times what is 32? The answer is 2. So a height of 2 and a base of 4 is what will give us the volume of 32, which is what we wanted, 4 times 4 times 2, and it will also minimize our surface area. And if you take these two values and plug them into our surface area equation, it'll tell you what that minimum surface area would be. These maximization and minimization problems are extremely useful we're only just touching the surface of what they can do. They can get much more complicated and help us even land spacecraft on other planets and things like that. So it's really valuable math, and hopefully you're actually enjoying it as we go through it. That concludes this section. We're going to look at some more applications of the derivative in the next section. If you have any questions, please let me know.